Okay, I mentioned the lake several times, so there it is, and we are now going to move into an energy balance model for the Earth as an example. This is very similar to what we did before in terms of the energy balance of averaging over the whole globe and looking for the average temperature we get. And we said if we didn't have an atmosphere, we got minus 18 degrees centigrade, which is much colder than the approximately 14-15 degrees centigrade of the Earth's surface temperature. And we added one atmospheric layer and showed that that would get very warm at 33 degrees centigrade, and then we looked at multiple levels. So we revisit the same calculation in a slightly different way here. We do it as an energy balance model in the context of climate modeling. So this will be a zero-dimensional model, so we average over the whole globe and look at one layer of the atmosphere as if it's uniform and has a same temperature. So either we have no atmosphere and we are receiving the energy from the sun and emitting out as we did before, or we have, for simplicity, one layer with energy coming in from the sun. But here we will add a slight bit of complication where we will add a cloud cover, because the real Earth has a cloud cover, and we will make some simple assumption that the clouds are complete black bodies, so they take the energy coming from the sun and they absorb it, reach whatever temperature, and they bounce energy up and down, and that the clouds have the same temperature as the atmosphere, so they are emitting at temperature T2 to space, right? So here the temperature from the surface and the emissivity temperatures are the same. Emissivity doesn't have to be 1. If it's a gray body instead of a black body as shown by this color, then it has an emissivity or absorptivity, and we know what a realistic range of emissivity should be. So keeping all that in mind, let's look at a point model of the radiation balance. It's similar to what we did before. We looked at the incoming energy being intercepted by a disk pi r squared related to the Earth's radius, and alpha is the average albedo for the whole globe. So you're averaging over the whole globe and looking at how much energy is being intercepted by the disk. So that gave us pi r squared times 1 minus alpha as 0, and what was being emitted to space, in this case no atmosphere, so it's just 4 pi r squared. Entire sphere is emitting outgoing long wave radiation, and the surface is gray, so has an emissivity of epsilon, planetary emissivity on average of 0.6, as we will see in a minute, and the black body the Stefan-Boltzmann relation is T to the 4th. Only addition we have done here is to say we will allow the heat content of the atmospheric layer to change in time. So 4 pi r squared is the layer covering the sphere, h is the vertical extent of the air layer, and rho is the density of air, and C is here the specific heat of air. Unfortunately, we also use C next as cloud cover, but just note that this is a Greek symbol C. So dt dt is the time rate of change of temperature, and if we set this to 0, then we get the equilibrium solution like we had before with emissivity. So radius of the Earth, vertical extent of the air, density of the air, specific heat of the air, globally averaged surface temperature, planetary albedo, solar constant energy coming in at the top of the atmosphere, planetary emissivity, and the Stefan-Boltzmann constant. This is our first parameterization. We are assuming that globally averaged atmosphere has height h of 8.3 kilometers. which is the average height of the tropopause if you average over the globe, and the emissivity, the emission of the to space of the long wave radiation is being done by the average temperature of this air, which has got the same temperature as well, it doesn't have to, it has the average surface temperature T, so its change is going to depend on the difference between the energy being received by the surface and energy being emitted by the surface. Okay, so if we then look for equilibrium temperature by setting the left hand side to 0, we are depicting what we saw before as slightly differently here. So we have a parameter choice. Planetary albedo is shown here going from 0.1 to 0.4. Think of the past with Ice Age, where planetary albedo would have been much higher, or a time during the dinosaurs when there were no glaciers anywhere and the planetary albedo would have been much lower. And then planetary emissivity is, let's say, unknown. Right now we can use satellites to estimate things like average planetary albedo and also average cloud cover. We haven't added cloud cover yet here. So we are able to choose planetary emissivity to match the surface temperature. So what happens? You can choose a different albedos and different emissivities to get different temperatures. So going from 60, 50, 20 down to 14, or you can go below to -10 as we would get if we had no atmosphere. So given the planetary albedo estimated from the satellite of 0.3, we can find the emissivity that gives us a realistic temperature of 14 degrees global mean surface temperature here. Then you have to see whether this planetary emissivity we are getting with our parameterization parameterized model here is realistic, and it turns out that the solution, equilibrium solution, looks like what we had before. T is 1 minus alpha S0 divided by 4 epsilon sigma to the 1/4. You just solve this equation, not a big deal. So in order to obtain a mean temperature of 14 degrees C in this energy balance model, this is just a zero-dimensional energy balance model, the planetary emissivity has to be set to epsilon of 0.6206, which is what you get if you go up to 0.3 and go in this direction to find the corresponding planetary emissivity. This is a value significantly lower than the emissivity of natural surface areas, which is around 0.8 to 0.99. Very bright, almost black, very dark and almost black body, or high albedo and down to 0.8. Hence, this model parameter is unrealistic for an average Earth surface and does not give any information about the processes leading to this radiative equilibrium. So when you parameterize and you choose values like this, it's called tuning. You tune the model to fit some observation that you are sure of, like the global average surface temperature. But then you have to have independent information produced by the model to make sure that it works. In this case, we derived emissivity which is not realistic. So we have to make it a little bit more complicated or sophisticated, let's say, which is where we add this cloud cover. So cloud is a complicated thing, as we saw already before. There are high clouds which allow short wave to come in and trap the outgoing long wave. There are tall clouds which are blocking sunlight but absorbing long wave. There is nighttime, daytime differences, middle cloud, low cloud, high cloud, and so on. So again, parameterizing everything together and writing the energy balance with part of the planet covered in cloud cover C, we have the energy being intercepted from the sun of pi r squared 1 minus alpha S0 as before, plus the surface is also receiving energy from the cloudy part of the atmosphere, because clouds are assumed to be black body and they are covering a fraction c of the 4 pi r squared of the sphere. So we are getting back to the surface c times 4 pi r squared times sigma T2 to the fourth, where T2 is the temperature of the atmosphere we have parameterized. Okay, very simple, make sure you understand. And that should be equal to 4 pi r squared epsilon sigma T1 to the fourth, which is the emissivity of the surface and the black body radiation of the surface. So net energy received by the surface is going to determine the gray body temperature of the surface, which is what this balance is saying. But we need another equation because we have two unknowns now. How do we do that? Basically, the amount of energy being trapped by the clouds is going to determine the temperature of the atmosphere. So that is equal to, again, cloud fraction of the surface area times the long wave energy being received by the clouds. So from the surface, that's the same term. That should be equal to energy emitted by by the cloudy area of the atmosphere, because it's emitting upward and downward. So 2 times c times 4 pi r squared times sigma t to the fourth. So that's the amount of energy that is being emitted by the cloudy fraction of the surface of the area of the atmosphere, because the rest of the energy is escaping to space. So that's the only amount of long wave energy being trapped by the atmosphere. So now you have two equations and two unknowns, and you can solve for T1 and T2, which are dependent on albedo, surface emissivity, and cloud fraction, or the area covered by clouds. We have gotten a better solution, but we have added a complication where we have now three parameters. We have cloud cover, we have albedo, and we have emissivity. Before we only had albedo and emissivity. We used realistic albedo and got an emissivity that was not very good. So now we use cloud cover as an additional parameter that we estimate from this satellite. I got a frog in my throat. This satellite data observation shown here, which on average is 0.6. So we add now a phase diagram to the solution. We're looking again at planetary emissivity. So we are going to fix the planetary albedo at 0.3 and look at the solution, the temperatures we get if we change planetary cloudiness. And again, we can change the average temperature T2 over a large range. But over the realistic value of 14 degrees C, we use planetary cloudiness value from satellites to go here and find that now the planetary emissivity we get is realistic. Plus, when we do this, the equation for T2 gives us a value of minus some degrees centigrade, I think minus 18 degrees centigrade if I'm not mistaken. Let me make sure. Sorry, T2 gives us minus 38.8 degrees centigrade, which is the realistic temperature we get at the average height of 8.2 kilometers, which is what we assumed for our atmosphere in our parameterized energy balance model. So you tuned the model using satellite data for albedo and cloudiness, but the model is proven to be realistic because it produces the emissivity temperature for the atmosphere at 8.2 kilometers of minus 38.8 degrees C, which is very realistic. Okay, so this is how we think about models and constraining the models, even in the simple case of energy balance model. Obviously, the energy balance model is not very realistic, but it's very instructive. It told us how the energy balance works. It told us how energy balance model can be used to estimate the emissivity temperature of a global mean atmosphere of 8.3 kilometers with surface emissivity that is realistic, as derived from using values that are realistic for albedo and for cloudiness from satellite data. Okay, so with this we'll move to more realistic model with equations and see how numerically the equations are solved, because these equations are nonlinear and cannot be solved analytically with paper and pencil, which is why we are discussing modeling and computer modeling and the grids and so on and so forth. Okay, I hope that's clear. Make sure you understand the equations, which are very simple, and the way we made the parameter choices, the tuning, and the way we validated the model. Okay.